Compounds have molar masses too. Their molar mass would be the mass of 1 mole of molecules. Each of the dishes in this picture contain 1 mole, that is 6.022 times 10 to the 23rd, of molecules. They each have a different mass that is characteristic of 1 mole of that particular compound. For example, the leftmost dish contains 256.5 grams of sulfur, which corresponds to the molar mass of the sulfur molecule. To calculate the molar mass of a compound, we would add up the masses of all the elements within the compound. For example, to find the mass of water, we would add 2 times the mass of hydrogen from the periodic table, plus 1 times the mass of oxygen from the periodic table. To find the molar mass of sodium phosphate, we would add 3 times the mass of sodium, plus 1 times the mass of phosphorus, plus 4 times the mass of oxygen from the periodic table. What is the molar mass of ethanol, C2H6O, in grams per mole? Is it A, 40.021 grams per mole, B, 29.018 grams per mole, C, 46.069 grams per mole, or D, 30.070 grams per mole? To find the molar mass of ethanol, we're going to take 2 times the mass of carbon plus 6 times the mass of hydrogen plus 1 times the mass of oxygen and add it up. So we have 2 times the mass of carbon, which is 12.011 from the periodic table. And then we're adding 6 times the mass of hydrogen from the periodic table, which is 1.008. And then we have 1 times the mass of oxygen, which is 15.999. So when we add those up, we get 46.069, which is C. When a compound contains parentheses, take the subscript on the outside of the parentheses and multiply it by the subscripts on the inside of the parentheses to find out how many of each element the compound contains. For example, to find the mass of magnesium nitrate, you would take the subscript of 2 and multiply it by the understood subscript of 1 on the nitrogen to get 2, and multiply it by the subscript of 3 on the oxygen to get 6. So you would have 1 times the mass of magnesium, plus 2 times the mass of nitrogen, plus 6 times the mass of oxygen from the periodic table, and add them up. Notice the magnesium does not get multiplied by 2 because it is not within the parentheses. Now that we know how to find molar mass of a compound, we can do our same gram to mole or mole to gram calculations, but this time with compounds and not just single elements. In this example, we are given the molecular formula of glycine and asked to find how many moles of glycine molecules are contained in 28.35 grams of glycine. Our first step is going to be finding the molar mass of glycine, because we are going to need it in our conversion factor in step 2. Our second step is using the molar mass to convert from grams of glycine to moles of glycine. Do not get confused by the wording of the problem. Saying moles of glycine molecules is the same thing as saying moles of glycine. We are not doing a mole to molecule conversion in this problem. In our first step, we calculate the molar mass of glycine by taking 2 times the mass of carbon, 5 times the mass of hydrogen, 2 times the mass of oxygen, and 1 times the mass of nitrogen, and adding them up. We come out with a molar mass of 75.067. In our second step, we take our grams of glycine and convert to moles of glycine by dividing by the molar mass of glycine. We start out with our known quantity, 28.35 grams of glycine. We choose a conversion factor with grams of glycine on the bottom to cancel out with our starting grams of glycine, and moles of glycine on the top since we are trying to solve for moles. We fill in the molar mass we solved for in step 1 next to grams, so it ends up going in the denominator. We do 28.35 divided by 75.067 and come out with 0.378 moles of glycine. We can also go in the other direction, from moles to grams. In this problem, we are given 1.42 times 10 to the minus 4 moles of vitamin C and asked to solve for the mass in grams. First, we would calculate the molar mass of vitamin C by taking 6 times the mass of carbon plus 8 times the mass of hydrogen plus 6 times the mass of oxygen from the periodic table and adding them up. We would come out with 176.124 grams per mole as the molar mass of vitamin C. Then we would use the molar mass as a conversion factor to go from moles to grams. First, we would start with the number we are given in the problem, 1.42 times 10 to the minus 4 moles of vitamin C. We would write a conversion factor with moles on the bottom to cancel out with moles in our starting number, and grams on the top since we are trying to solve for grams. We fill in our calculated molar mass next to grams, so it goes in the numerator this time. We do 1.42 times 10 to the minus 4 times 175.124, which gives us 0.0250 grams of vitamin C. In this example, we are told that we have a 40.0 milligram sample of saccharin and are asked to find molecules of saccharin and number of carbon atoms in the sample. We are given both a molecular formula and a structural formula. From either of those, we could calculate a molar mass. To shorten this problem a little, the molar mass has been provided for you, 183.18 grams per mole. You should not always assume that it will be provided. Another way that this problem has been simplified for you is that the mass has also been provided in grams, not just milligrams. If the mass were not already in grams, you would need to get it into grams. The molar mass only works as a conversion between grams and moles. To solve this problem, we are going to go grams of saccharin to moles of saccharin by dividing by the molar mass of saccharin, then moles of saccharin molecules to number of saccharin molecules using Avogadro's number. Once we have number of saccharin molecules, we can add on one last step to find how many carbon atoms are in the sample. First, we start with the number given, which is 0.0400 grams of saccharin. We write a conversion factor with grams of saccharin on the bottom to cancel out with the grams we started with, and moles of saccharin on the top, since moles is our first intermediate step we are trying to go towards. We fill in the molar mass of saccharin next to grams and 1 next to moles. We can add on a second conversion factor, which will have moles on the bottom to cancel out with moles in the top of our first conversion factor, and it will have molecules on top, since that will be the answer to the first part of the question. We fill in Avogadro's number next to molecules and 1 next to moles. That tells us we are doing 0.0400 divided by 183.18, then times 6.022 times 10 to the 23, so we come out with 1.31 times 10 to the 20 molecules of saccharin. To go from molecules of saccharin in the sample to atoms of carbon in the sample, we will use the relationship that each molecule contains 7 carbon atoms. We set up our conversion factor with molecules of saccharin on the bottom and atoms of carbon on the top. We fill in 7 next to our carbon atoms and 1 next to our molecules of saccharin. That tells us to multiply by 7, and we come out with 9.20 times 10 to the 21 carbon atoms. I'd like to end the chapter with a few jokes about the mole. The mole is so important to chemists that there's even a mole day that chemists celebrate on October 23rd, 1023. What is a word for chemical nonsense? Molarchy. What does Avogadro wear when it is cold? Thermal underwear. Where did Avogadro stay on vacation? A mole-tel. What did Avogadro teach his students in math class? Multiplication. How did Avogadro get through the desert? On a camel. Why is Avogadro so rich? He is a multimillionaire. Why was there only one Avogadro? When they made him, they broke the mold.